Let's talk a little about forces and moments and how to really solve equilibrium questions. Forces. So, um, as far as forces, you know from Newton's second law, that the net force, or the sum of all individual forces, equal to ma. And we know that if an object is in equilibrium, mechanical equilibrium, so it's not moving, then we know that there's zero acceleration. So the right side becomes zero, which means that the net force is equal to zero. So when you have an object and you add all these forces together, they should equal zero. And they equal zero because you choose it that one direction to be positive and another direction to be negative as far as the vertical and horizontal axis. So if we take, any force to the right and up as positive x is this way, positive y is that way, any force pushing to the right is going to be positive. So let's just say 5 newtons. And any force to the left is going to be negative. So let's just say this was negative 8 newtons. And then the sum, or the net force, in let's just say the horizontal axis or x-axis, would be 5 plus negative 8, or just 5 minus 8. So you would have negative 3 newtons. And since it's negative, we know that negative points to the left. So if you want to write this in words, 3 newtons to the left. So that's balancing forces in equilibrium. So moments. So the moment of an object, or if you really want to write its torque, I'll just leave it as this tau symbol, is just the force times the distance. Well, this will really be the perpendicular. Okay, so I'll explain what that means in a sec. It's perpendicular force times the distance from um, whatever point you want. You can choose any point and take the torque or moment about that point. So what does this perpendicular force mean? So if you have point here, so you got something like this, and your force is acting downward, okay, 10 newtons, and this is a distance of 5 meters. Now you can't just quickly jump into it and say, okay, it's force times distance, so it's 10 times 5, so it's 50 newton meters. The reason is we only care about the force that actually causes the turning. Okay, so that's what the moment and torque are for. Only forces that cause the turning. So when you push down, there's really a force pushing this way, so that causes the turning, clockwise turning, and there's a force pushing this way, and that does nothing. That does not affect the turning in any way. So this is why you can't use the 10 newtons. We need the component that's pushing perpendicular to the surface at 90 degrees. The problem is, a lot of times they won't tell you that. Will just give you this distance. So they'll tell you, okay, this is 4 meters. So you can just take the force from here. It's still going to be, so when you're pushing from here to here, it's still going to be 10 newtons down. That's not going to change throughout this whole way. And now you got a perpendicular force, 90 degrees to the line to whatever point you care about. So now you can just do 10 newtons times 4 meters, 40 newton meters. Sorry. And we know that in equilibrium, any any moment causing, a rotation clockwise has to be equally balanced with a rotation going counterclockwise. Because in equilibrium, so if you have something like this, like a beam, there's two forces like that. Okay, we know that the sum of the forces down equal the sum of the forces up. So so this force plus this force has to be equal to the force supported by this little fulcrum over here. Because if it wasn't, if the net force was not 0, then we know that the object would be accelerating, and we know it's not because it's in equilibrium. So the net force has to be 0. So this force plus this force plus this force is equal to that force. And also, if you take this point point of interest, the one that you care about, then we know that this force is going to cause clockwise rotation, so a clockwise moment or torque. And this one is going to cause a counterclockwise, and those have to balance out because we know that this beam is not moving. Because you can show that if there was a net force, so even if it was slightly, then the beam should always the beam should tip over until, I guess, it reaches the ground. So those are the two key things that you need to remember, and with these you can solve all the problems we have that were given in the slides and everything. So balance forces, so horizontal and vertical if needed, you can do those separately, plus balance moments or torques, whatever you call them. And then with this alone, you can solve all the questions. And if you want to really see what it looks like if you were to write something, so let's just say we were trying to balance the forces in the x direction, you'd write something like this. So a net force in the x is equal to, and then you just add your force. So force 1, force 2, plus blah blah blah. And then you can always write this is equal ma. So it's equal, so just in the horizontal, so this way. The net force is the addition of all the horizontal forces, or the horizontal components, which is equal to the mass of the object times the acceleration in the horizontal direction. And we know in equilibrium that's 0. And then second, we know that, so that torque, if we were, or we can just, if you want to, you can just put the moment causing clockwise rotation is equal to the, or you know what, the net moment, or net torque, is equal to the torque from the clockwise rotation plus the torque from the counterclockwise rotation. And you can choose one of these to be negative. Usually counterclockwise is chosen to be positive, and then this is chosen to be negative. So you'll get something like this. So you get force that causes the clockwise rotation times the distance from the clockwise force to whatever point. So in this case, we use the fulcrum in this example, plus the force that causes the counterclockwise rotation times the distance from that force to your point of interest.